Quantum physics is often thought of as confusing, but it doesn't have to be. In fact, I think we could formulate one of the founding principles of quantum physics in the next few minutes. Today, I want to talk to you about black body radiation. No, don't run, it's okay. A black body is just an object in space that absorbs all of the energy you throw at it. A good example of this might be a hole in the side of a box. No matter how much light you shine at that hole, it'll still be a dark hole, and it won't heat up or light up. You won't be able to change its color by shining a light at it. The only special thing about a black body is that it must be in thermal equilibrium with its surroundings. Here are a couple pieces of fundamental physics to help you understand what I just said.
Light bulbs produce light, as we know. But what is light? Light consists of waves of energy called radiation, produced in this case by heating a filament inside our light bulb. But light is not the only form of radiation. There are all sorts of radiation: infrared, ultraviolet, all the visible light in between, and more. Now, what makes these types of radiation different? Well, that is their frequency, a measure of wavelength. There are all sorts of different radiation, from harmless microwaves to ultraviolet waves, then to dangerous gamma waves beyond that. Microwaves have a very low frequency and are less dangerous, plus require little energy to create, whereas gamma waves have an extremely high frequency, are extremely dangerous, but require tons of energy to create. Gamma waves are only dangerous because of their short wavelength, and therefore their high frequency. Visible light is only a small part of this spectrum of frequency, and it is between infrared light at the low end and ultraviolet light at the high end. But all of these different frequencies of light have one thing in common. They are all absorbed by a black body when shone on it from any angle. What is thermal equilibrium? Well, funny you should ask, because it was the second principle of science that you needed to know. Thermal equilibrium is portrayed here quite well with this toaster oven. Now, what the toaster oven is doing is heating up the air inside of itself to about, 154 degrees Celsius, which is quite warm. But the bread is only 11 degrees Celsius, because I just pulled it out of the freezer. So, what happens is that the temperature of the air around the bread drops and the temperature of the bread itself rises until they're the same temperature, or in other words, have reached thermal equilibrium with each other. Now your bread is toast.
Now for the ultraviolet catastrophe. This is how classical physicists Lord Rayleigh and James Jean interpreted blackbody radiation. Classical physics explains blackbody radiation very poorly, because it suggests that as frequency increases, so do the radiation intensity and temperature by exponential amounts. This is really bad for us. The experimental data showed this graph, but with Rayleigh and Jean's interpretation, it would have to look something like this. What this meant is that even the smallest amount of radiation, for example a moment in front of the fireplace, would be enough to kill you. Now you're probably thinking, what was done about this terrifying theory? Well, a physicist named Max Planck came up with the correct solution for blackbody radiation. What he said is that as frequency increases, the number of wavelengths emitted actually begins to drop, eventually to zero. So you have a super hot object at high frequencies emitting no radiation, which means it's black. And if this object is in thermal equilibrium with its surroundings, it will stay that way. And it is constituted as a perfect black body. Quantum physics is everywhere throughout our universe. It's in our light bulbs and our toaster ovens. And so I hope this video has inspired a genuine curiosity in you for quantum physics.